Hey there. So, if you're deep into studying engineering or chemistry right now, just go ahead and take a breath. Seriously, let's step away from those massive walls of text for a minute. Today, we're going to look at a pretty fascinating and honestly kind of quiet natural phenomenon. We're talking about something that happens silently all around us, literally every single day, turning solid metal back into the earth. In this explainer, we're going to gently unpack the mystery of waterline corrosion. Let's just dive right in with a question that might sound super specific, but I guarantee you've seen it out in the real world. Have you ever noticed an old steel water tank, or maybe just a metal bucket left out in the garden half filled with water? If you actually look closely at it, the heavy rust doesn't happen on the dry metal up top, and kind of surprisingly, it doesn't happen way down at the very bottom either. The really aggressive decay blooms right below the water surface. So why does the metal decay so unevenly? Like, what invisible force is drawing a literal line right at the water's edge? Well, to answer that, we need to introduce our core concept for today. You'll probably see this written in your textbooks as differential aeration corrosion. And yeah, I know that sounds like a super heavy piece of academic jargon, but let's break it down because it's actually really simple. Differential just means different. Aeration simply refers to the amount of air, or more specifically, oxygen. So all this intimidating term means is that a single piece of metal is being touched by different amounts of oxygen at the exact same time. When nature senses that kind of imbalance, it immediately tries to resolve it. And that resolution, that's exactly what we call corrosion. This really illustrates exactly how that imbalance is created. Think about the water inside a steel tank. Above the waterline, the steel is completely exposed to the open air, right? It's just bathed in oxygen. But below the waterline, the water itself acts as a physical barrier. The dissolved oxygen in the water is way lower than the oxygen up in the open air. So just by holding water, the tank has created this dramatic divide. You've got high oxygen above and low oxygen below. Okay, so here is the crucial part. What actually happens next? This difference in oxygen turns our one single piece of steel into an invisible wet battery. It's crazy. Let's look at the two zones side by side. The part of the metal above the water, the side with all that oxygen, becomes what chemists call the cathode. In this type of hidden battery, the cathode is the protected zone. It stays totally safe. Meanwhile, the part of the metal sitting just below the water, the oxygen-starved side, becomes the anode. And the anode is the part that takes the hit. It basically sacrifices itself. It dissolves, it rusts, and it corrodes. Now keep in mind, this isn't just a thing for massive industrial water tanks. This quiet little divide happens on literally any partially immersed metal. Take a simple metal rod resting in a beaker of electrolyte solution. The top part sticks out into the highly oxygenated air, while the bottom part is submerged. The exact same chemistry applies here. The less aerated bottom portion becomes the anode and starts to decay, while the top portion becomes the cathode and stays completely protected. The metal is basically fighting against itself simply because of the air around it. Let's walk through how this builds into the actual mechanism of wet corrosion. Think of it as a gentle, continuous current. Really, it's just a three-step dance of electrons. First, down at the oxygen-starved anode, the metal begins to dissolve, which liberates free electrons. Second, those newly freed electrons flow upward through the solid metal itself, almost like it's a wire, seeking out the cathode. Third, when those electrons finally reach the highly oxygenated cathode above the water, the oxygen and water just use them up. As long as this flow keeps going, the metal below the surface is slowly eaten away. Now, if you're preparing for an exam, you are definitely going to need to know the chemistry here. But please, don't let these equations intimidate you. They're literally just the mathematical translation of those three peaceful steps we just talked about. Down at the anode, the solid metal, which we just represent with the letter M, turns into dissolved ions, releasing those two little negative electrons. That's oxidation, that's the decay. And up at the cathode, half an oxygen molecule, some water, and those two traveling electrons combine to form hydroxide ions. That's reduction, which gives us the protection. It's a perfectly balanced, continuous loop of cause and effect. All right, Section 1, the sunken ship paradox, a depth exception. Let's see how our new mental model holds up in the real world. So check out this surprising fact drawn directly from our engineering sources. You would probably think that a massive steel ship resting at the bottom of the ocean would be entirely eaten alive by rust over the years, right? But the source explicitly notes that ships sunk underwater for several years actually do not undergo corrosion from differential aeration. This is one of those things that usually stops students in their tracks. Like, how in the world can something that is completely submerged in water not suffer from this type of waterline rust? Well, the answer beautifully validates the exact rule we just learned. Think about the environment way down at the bottom of the ocean. It's deep, and the oxygen concentration down there is incredibly uniform everywhere. There's no waterline at all. The difference in oxygen between the top of the sunken ship and the bottom of the ship is just negligibly small. And remember our very first rule? Without a difference in oxygen, that invisible battery cannot form. Without the anode and cathode divided by an oxygen barrier, the differential aeration corrosion simply loses its power. Boom, no battery, no rust. Moving on to Section 2, Peaceful Prevention, Restoring the Balance. Because now that we know exactly how it works, we can figure out how to stop it. Engineers actually use several really clever, low-pressure methods to protect metals from themselves. The most obvious one is just to apply a physical barrier, like metallic or chemical coatings that prevent the environment from touching the metal at all. We can also make sure the material maintains its own natural microscopic protective film. But honestly, my absolute favorite method is something called cathodic protection. Remember how the anode always decays to protect the cathode? Well, engineers will literally suspend a block of a more reactive metal, something like zinc or magnesium, right inside the steel water tank. This new metal willingly volunteers to be the anode. It completely sacrifices itself, slowly dissolving away, just so that the entire steel tank becomes a protected cathode. It's a really beautiful, engineered act of chemical sacrifice. As we wrap up this explainer, I just want to leave you with a slightly different perspective. It's so easy to look at a rusted water pipe or corroded tank and just see destruction, or, to look at a textbook and just see stressful equations. But I really hope today you've seen the elegant logic behind all of it. Next time you notice that orange bloom of rust creeping just below a waterline, I hope you don't just see decay. I hope you see the quiet, invisible battery at work. It's a remarkable balancing act of electrons and oxygen, silently translating the laws of nature right in front of your eyes. Keep studying, keep observing, and just take it one step at a time. Catch you next time.